We have gone through the subject. Hello everyone. Already we have gone through the three lectures. I think you should get some basic knowledge about the subject, right? So in this today's class, we are moving to the signals. That is classification of the signals. Okay. So what about the classification of signals? So, what are the types of signals? So, first we should see that what are the classification of signals. So, in some signals we will have both continuous and discrete, and some signals there is no the types between continuous and discrete time signals. So, we will learn one by one so that we will get that thorough. We will thorough that topics. Okay. So, problems will I will teach you in later classes. So, first we will study that got this theory. So first is analog and digital signals. Next, continuous and discrete time signals, periodic and aperiodic signals, odd and even signals, energy and power signals, deterministic and non-deterministic signals. So these are the classification of signals. So we will going to see one by one in the all signals in detail. Okay. First of all, that is analog and digital signals. Analog signals is signals that is defined at every instant of time. So in first class itself, I have said that the analog signal is a continuous time signal. So that is it is defined for every instant of time is known as analog signals. Analog signals are continuous in amplitude and time. So it is the amplitude and time is continuous. So it is denoted as x of t and it is also known as continuous time signals. So it is denoted by x of t and it is a continuous time signal. So from it's a sine waveform. From the waveform, we can see that it's a continuous time signals. Okay. Next, digital signals. So signals that are discrete in time and quantized in amplitude is called digital signals. So in second class, I think I have said that the analog signal is converted into digital signals in the forms of zeros and ones, right? So the digital form of signals, so signals that are discrete in time, so it is not continuous. So the amplitude and the times are continuous. It's a discrete in time and quantized in amplitude is called as digital signal. So this is the general representation of the signals. So it's represented. Say here there is no waveform. So zero. Here it is one. So zero one. It will go on repeated. So if there is no signals present, zero zero. So there is two zeros and one zero. Okay. So this is the basic representation of the digital signals. Okay. Continuous and discrete time signals. Continuous time signals. So a signals that is defined for every instant of time is known as continuous time signals. So continuous time signals are continuous in amplitude and continuous in time. It is denoted by x of t. So first of all, it's an analog signal. We have studied that analog signals and digital signals. Here we are going to study about continuous signals and discrete signals. Okay. So in continuous signals, so signal that is defined for every instant of time. So this is the best examples. So analog signals and the continuous signals both are same. So here there is it's a defined for continuous. It's a continuous in amplitude and continuous in time. It is defined as x of t. Both are same. Okay, analog signals are continuous signals. Next, discrete time signal. So the signal it is defined for discrete instant of time. So it is not continuous. It is discrete. So from this waveform itself, we can know that x of 0 that is 1 the value is 2, x of 1 that value is 2, x of 2 the value is 3, next x of 3 the value is -4, x of 4 the value is 6, right? So the signal that is defined for discrete instant of time is known as discrete time signals. The discrete time signal is continuous in amplitude and discrete in time. It is also obtained by sampling a continuous time signal. It is denoted by x of n. Okay, so it is not continuous in nature, it is discontinuous in nature. So the amplitude and its time also it's a discrete in nature. It is also obtained by sampling a continuous time signal. It is denoted by x of n. Okay, next, even and odd signals continuous domain, that is symmetric and anti-symmetric signal continuous domain. So we will see that first continuous time and next we are going for that is the discrete time. Okay, I have already explained that if it is continuous it will represent it as in d format. It is continuous time, right? So this signal that exhibits symmetry with respect to t equal to 0 is called even signal. So, for example, in even signals, we should satisfy this condition. So, signal should satisfy this condition, that is x of t equal to x of minus t. Okay, so this is opposite for the odd signal. So, this is the signals that exhibit anti-symmetry. So, even signal is a symmetric signal. So, both sides are equal, but the odd signals is an anti-symmetric signals. Okay, right? So with respect to t equal to 0 is called odd signals. Odd signals satisfies the conditions x of t equal to minus x of t, x of minus t. Okay, right. So that means it is an anti-symmetric signal. So both sides are not equal. So here we can see that x of t equal to minus into x of minus t. So this both signals are not equal. So if it is neither odd nor even, so if it is odd function, we can even function we can calculate by using x of t equal to x of minus t. If it is odd function, we can calculate x of t equal to minus into x of minus t. So by calculating even, and for example, if they given and one signal, okay, by is in this signal we have to calculate the even part and odd part. So how will you calculate the even part and odd part? So by using this formula, x e of t equal to 1 by 2 x of t plus x of minus t. Okay, odd part x naught of t. X naught means x odd of t equal to 1 by 2 x of t minus x of minus t. So this is the odd and even part of the signal. Okay. So next, even, that is symmetric and anti-symmetric signals in discrete domain. That is even signal. A signal that exhibits symmetry with respect to n equal to 0 is called even signal. Even a signal satisfies the condition x of n equal to x of minus n. Okay, odd signal. So the odd signal is the same here. In continuous time domain, what will happen? That is x of t equal to x of minus t. This is the situation we have to satisfy the conditions, and order signal x of t equal to minus x of minus t. Next, a signal that is satisfies symmetry with respect to n equal to 0 is called even signal. So even signal should satisfy the condition x of n equal to x of minus n. Okay, so odd signal. So odd signals already we have studied in, that is a continuous time signal, that is an anti-symmetric signal. That is both sides are not equal. With respect to n is equal to 0 is called odd signals. Odd signal satisfies the condition x of n equal to minus x of minus n. So the even part x e of n and the x naught of n of discrete time signal x of n is even part x e of n. So even part, how will you find out the even part and odd part of the signal? So even part x e of n equal to 1 by 2 x naught of n plus x of minus n. So how will you find out the odd part? So 1 by 2 x of n minus x of minus n. This is the formula for find outing the even part and odd part of the corresponding. So if we are find out, so find out the odd part and even part of signal. So we will study the problems in further future classes. So just go through or study these formulas. Okay. So these are the conditions. So we first we should satisfy the condition. If it is an odd even signal, we should get even part. If it is an odd signal, so it should satisfy the condition x of n equal to minus x of minus n. Okay. So that's all about the even part. So we have studied three signals, right? Analog and digital signals, continuous and discrete time signals, even and odd signals in continuous domain and in discrete domain. Okay. Periodic and aperiodic signals. So in this aperiodic and periodic signals, there are two in this even part, and see in periodic and aperiodic is also we will find out in continuous domain and in discrete domain. Periodic signal. A signal is said to be periodic if it repeats again and again over a certain period of time. Okay, periodic means it is continuous in nature. So if it is a period, a system is said to be a periodic signal, it repeats again and again over a certain period of time. Okay, aperiodic signals. A signal does not repeats at a definite interval of time is called aperiodic signals. So it does not repeated over. So it is a discontinuous signals. Okay, not repeat at a definite interval of time is called aperiodic signals. Okay, so what about that periodic and aperiodic condition in continuous domain and discrete domains? We will see. Okay, so continuous domain. In continuous domain, time signal is said to continuous time signal is said to be periodic if it satisfies the condition. So if it a signal is said to be periodic it should be periodic in nature, right? It will repeats over again and again in certain period of time. If it is satisfies the conditions x of t equal to x of t plus t, where t is a fundamental time period. The above condition, if it is not satisfied, it is not a periodic signal, it is said to be aperiodic. So it's a fundamental period. Here t is, here the t is mentioned as t is equal to 2 pi divided by ohm. So here ohm is the fundamental angular frequency in radian per second. Okay, so this is the periodic and aperiodic signals in continuous domain. Next, we are going to see about the periodic and aperiodic signals in discrete domains. What will happen in the discrete domain? A system is in discrete domain we will know that we will mention is x of n, right? So in discrete time signal is said to be periodic if it satisfies the condition x of n equal to x of n plus capital N, where n is fundamental time period. So n is written as here. In continuous time domain, we will see that capital T is written as 2 pi divided by ohm, and ohm is the fundamental angular frequency, right? So the discrete time signal is said to be periodic if it satisfies the condition x of n equal to x of small n plus capital N, where n is the fundamental time period. If the above condition is not satisfied, then the signal is said to be aperiodic fundamental time period. N is equal to 2 pi m divided by ohm. So here ohm is the fundamental angular frequency, and m is the smallest positive integer. That makes n as positive integer. So we will study in the future classes about the and we will solve the process of if we solve the problems we will get the better knowledge about that uh, all the signals. Okay, here it's just a definition and formulas about that periodic, aperiodic, even, odd, angular, I mean angular not, it's a analog, digital, and a continuous and a discrete time signals. Okay, next, it's energy and power signals. Energy and power signal is very very important for the examination point of view and the point of view. Okay, energy and power signals. So the signals which has finite energy, so energy is finite. Okay, if it is an energy signal, energy should be finite, all right? If it is a finite signal, we can identify that finite amount of energy. And zero average power, so its power is zero, is called energy signals. So energy signals is normally non-periodic signals, like exponential signals will have constant energy, and also non-periodic signals or energy signals. So it's not a periodic signals. So we will get the energy signals. So energy signal should lies from 0 to infinity, and power is 0. So here it is itself it's mentioned a signals which has finite energy and zero average power is called energy signals. So the non-periodic signals like exponential signals will have a constant energy. Exponential signals will have constant energy. So non-periodic signals or energy signals. For energy signals, 0 less than E less than infinity and P equal to 0. For continuous time signal, energy E equal to limit t tends to infinity integration minus t to t modulus x of t the whole square into dt. So this is the formula for continuous time signals. Okay, so I think we should buy out this continuous time cycle, that's formula. So limit t tends to infinity, some of the formulas are there, we should learn the formulas. Okay, limit t tends to infinity integration minus t to t modulus x of t the whole square into t dt. This is for here it's a t is present, so it is a continuous time signal. So in terms of discrete time signals, how will you represent the energy? So energy E equal to limit n tends to infinity summation n is equal to minus n to n modulus x of n the whole square. Okay, so this is the energy signals. Power signals, the signals. Next, the signals which has finite average power. If it is a power signals which has a finite average power and energy is infinite energy is called power signals. The periodic signals like this. So power signals are periodic signal, but energy signal is non-periodic signals. But power signal is periodic signals like sinusoidal complex exponential signals will have constant power, and so periodic signals or power signals. For power signals, 0 less than p less than infinity and e equal to infinity. So for an example, for continuous time signals, average power p equal to limit t tends to infinity 1 divided by 2t integration minus t to t modulus x of t the whole square into dt. Okay, For a discrete time signal, average power P equal to limit n tends to infinity 1 divided by 2n plus 1 summation n equal to minus n to n modulus x of n the whole square. These are the formula for continuous time signals and discrete time signals. One difference is in the average power there is 1 divided by 2t is present compared to energy signals, and here there is 1 divided by 2n plus 1 is present. Okay, so if you study one formula, by using that formula we can extract the another formula, so don't need to worry about that. Okay, so that's all about the energy and power signal. This is very important and very important formulas. By solving the formula we will get the more knowledge and more idea about that signals. Okay, deterministic and random signals. Okay, deterministic signals means here there is a we can't predict that there is no certainty over the signals at any instant of time. That is, its instantaneous value can be predicted. It can be represented by mathematical equation. So one of the advantage is it can be predicted represented by using mathematical equation. For an example, sinusoidal signals. So there is uncertainty over the signal at any instant of time. That is, it is instantaneous values can be predicted. We can predict the value. So it can be represented by mathematical equation, that is sinusoidal signals. Okay. Random signals. Random signals means there is uncertainty over the signals at any instant of time. That is, instantaneous values cannot be predicted and yet cannot be represented by mathematical equation. The mathematical equation is not be represented. For example, noise signals. For example, we can is it able to find out the mathematical equation for the noise? So it's very difficult to find out the noise. Find out the mathematical equation, right? So it's a random signals, or it is also known as non-deterministic signals. Okay, that's all about the deterministic. Mostly the we don't have the problems in randoms and that means deterministic and non-deterministic signals. Causal and non-causal signals. The continuous domain. A signal is said to be causal if it is defined for t greater than or equal to 0. That is, x of t equal to 0 for t less than 0. Okay, this is causal signal. So causal signal is it is defined for t greater than or equal to 0 and x of t equal to 0. Non-causal signal. A system is said to be non-causal signal if it is designed for t less than 0 or for both t less than 0 and t greater than or equal to 0. If x of t not equal to 0, if it is equal to 0 and it is defined for t greater than or equal to 0, for t less than 0, it is known as causal system. A system is said to be non-causal system if it is defined for t less than 0 or for both t less than 0 or t greater than or equal to 0. That is, x of t not equal to 0 for t less than 0. When a non-causal signal is defined only for t less than 0, it is called an anti-causal signals. So non-causal signals will it is defined only for t less than 0. So it will define only for t less than 0 and it is called an anti-causal signals. Okay. So in discrete domains, what will happen? So in discrete domains, the causal signals is system is said to be causal. So if it is instead of t, we will it will in discrete domains we will present n. Okay, n greater than or equal to 0. That is, x of n equal to 0 for n less than 0. And for not what will happen in non-causal signal? A system is said to be non-causal if it is designed for n less than 0 or for both n less than 0 and n greater than or equal to 0. That is, x of n not equal to 0 for n less than 0, when a non-causal signal is defined only for n. Okay, so its causal signal is defined only for t, right? Less than 0. So that's all about the classification of the signals. So it's just an overview of the subject or overview of the signals. Okay, classification of signals. So if we solve the problems one by one, we will get an more idea about that subject. Okay, so that's it. Thank you.